Welcome everyone. Welcome aboard. This is Monday Dennis Max bringing you the S4 physics, and this time we are bringing the favorite of all for the students. According to my experience in the teaching profession, I realized that this is a topic that students like most, and it's none other than the modern physics. The physics that really helps you understand so many things that are so interesting. I won't explain a lot, but I want us to dive straight into the subtopics that we shall handle. We shall deal with atomic models. Here we're going to put emphasis on the nuclear and the atomic structures. We're going to look at the nuclear processes, which shall involve nuclear fusion, nuclear fission, and radioactivity. We shall look at cathode rays, X-rays, and the photoelectric emission shall sum up the topic. Now, some little introduction, some background to the first part. You know very well that before this type of physics, people looked at objects just the way they are and the way they were, big sized objects. But then about 2,500 years ago, that's in I think around the 5th century BC, the ancient philosophers Democritus and his teacher Leucippus were the first people to talk about atoms. How did they do that? Now they came to a conclusion that this S ought not to be here, that if you split an object continuously, at a certain point you end up with the smallest pieces that can no longer be split. So it's like they assumed if you have an object and you cut it into half, and you cut that half into more halves, and you keep splitting, a point reaches, or at a certain point, you will have pieces that can no longer be split. Now, according to them, Democritus called the smallest indivisible particles atomos, A-T-O-M-O-S, a Greek word translated as uncuttables. So he said that those smallest indivisible particles, they are called the uncuttables. And in Greek, that is atomos, from which we derive the word atom. So the word atom is thus derived from the Greek word atomos. You can say atomos or atomo, which means uncuttable. Now, Democritus imagined that different objects are made up of different atomos or uncuttables of different shapes and sizes. And when the famous philosopher Aristotle the Great proposed his idea of what matter was made up of, Democritus's ideas were ignored by philosophers and scientists for many centuries. Now, Democritus had a good idea. According to him, he said that matter or objects were made up of these atomos, the smallest indivisible particles. And according to him, he said that they had different shapes. For example, he said that for iron, that they had hooks that held them so strongly together. But when the great philosopher Aristotle, because of the great advances he had done in philosophy, when he made his own ideas about what matter consisted of, the ideas of Democritus and Leucippus were ignored for very many centuries. And so Aristotle said that different things were made up of different amounts of the elements earth, water, air, fire, and ether. And more people believed Aristotle. Yet Democritus and his teacher Leucippus had a point. Now, the idea about matter remained that way until 1808, when John Dalton, a British chemist, came up with the first scientific experiments that show that matter was made up of tiny little particles, the indivisible atomos. Now, it was in 1808 when John Dalton brought to light the ideas of Leucippus and Democritus, which they had proposed in 5 BC or 4 BC actually. And according to him, according to John Dalton, who was a British chemist, he performed experiments, and he really proved that matter was made up of tiny little particles, the indivisible atoms. So John Dalton imagined atoms as tiny little spheres that are arranged in different combinations to make different things. He said that atoms are indivisible. So he brought the idea of Democritus back to light scientifically. But according to him, he said that there were spheres. They were just like balls, hardy balls, those atoms. He didn't even imagine that there were charges. As in, we're looking at just the process of discovery of these atoms. Now, it was in 1904 when J.J. Thomson performed experiments from which he found out that atoms were not indivisible as stated by Dalton. They were not just like balls, like hard spheres, as Dalton had stated. So Thomson found out that atoms contain small negative particles which he called electrons. So he came up with the plum pudding model, in which he stated that atoms contain negative particles, which we call electrons, which are randomly arranged in a positive pudding, just like a guava. Now, just for example, in a Ugandan setting or in the East African setting, imagine a guava. And you know how seeds can be just randomly arranged there. If you know blueberry, it also works. Yeah. So for him, Thomson said that atoms consist of, they're like a guava. And an atom is like a guava, and it contains the electrons. The electrons are like the seeds that are just randomly scattered within the positive. The positive succulent part of the guava would be like the succulent part of the guava is analogous, or is compared to the pudding, according to him, when he proposed the plum pudding model for J.J. Thomson. He said that, now if you look at a guava, I think I'll make some little drawing here. Okay, he said that if you have a guava here, now like the seeds inside there, those are the electrons, and then this other thing, the succulent part is positively charged, and then these that are just scattered there, these are the electrons randomly arranged. That was according to Thomson in 1904. In 1911, Ernest Rutherford, together with Hans Geiger, these were his partners, Hans Geiger and Ernest Madsen, performed experiments. And the experiments were basically the gold foil experiments, from which they discovered that the positive charge of an atom is concentrated in the middle of an atom. Now for them, Rutherford found out that this positive charge was not just scattered all over, was not just like according to the plum pudding model of Thomson, J.J. Thomson. J.J. Thomson said that, because when he proposed the plum pudding model, for him he said that an atom is made up of a positive pudding in which they just scattered negative electrons. But then Rutherford and Hans, together with Marsden, they performed experiments using gold foils, from which they discovered that the positive charge of an atom is concentrated in the middle of an atom. So they called the dense positive part of the atom the nucleus. So the nucleus was discovered by Rutherford. And Rutherford's model is sometimes called the nuclear model of an atom. And that was in 1911. Some little history we're coming. So Rutherford's model, or the Rutherford model, is sometimes called the nuclear model of an atom because he discovered the nucleus. So it was in 1913 when Niels Bohr reasoned that the electrons spin around the nucleus in circular orbits, and in 1919 he discovered protons. Now you see. So in 1932, James Chadwick discovered neutrons. So what we're going to look at as the atomic structure, or the structure of an atom, was as a result of very many discoveries by different scientists over very many centuries. But then you look at this, that according to Niels Bohr, for him, he said that electrons were not just arranged randomly, like Thomson had suggested, and like Rutherford had also suggested and maintained actually. But Niels Bohr reasoned that electrons spin around the nucleus in circular orbits. And in 1919, he also discovered that there were protons. But he didn't know that they were electrons. That they were neutrons. It was in 1932 when James Chadwick discovered the neutrons. Now, when discussing atoms, we shall consider the modified and simple model of Bohr, which we call the simple Bohr's atomic model. But that's not the most accurate model. There is another more advanced model, but for now, it is a quantum physics model, which does not consider orbits, but it considers orbitals. For those of you that will be interested in furthering your understanding in physics, you'll find it at higher levels of learning. For now, we shall maintain a simple model, which was suggested by Niels Bohr. So let's look at the atomic model, and this is the Bohr's model of the atom. An atom consists of a small dense nucleus at its center. This is the model. The electrons rotate about the nucleus in circular orbits, and the orbits are also called energy levels, or sometimes called shells. The innermost energy level consists of at most 2 electrons, so it cannot exceed 2 electrons. Electrons in the inner energy levels possess less energy than those in the outer energy levels. And the nucleus consists of protons and neutrons. The protons are positively charged. The neutrons have no charge. The electrons are negatively charged. And in an electrically neutral atom, the number of protons equals to the number of neutrons. If you're asked to describe a simple model of an atom, this is what you have to state. You state the composition of the nucleus, talk about the nucleus, its composition, talk about the electrons spinning or rotating about the nucleus in circular orbits, and you go ahead and talk about the charges of each, and you'll be done. Now, let's look at this. So I've represented here red is, I have here some particles. So the red particles here together with the blue particles, I represented the red particles, as you can see them, as the protons, and then the blue ones as the neutrons. And together they are forming the nucleus. So we have the first energy level here, in which we said there should be a maximum of 2 electrons. So you see the first energy level here, and there are 2 electrons. And then we can have a second energy level. This one can take up to a maximum of 8, and so we can move on just like that. There is another energy level still with more electrons. Now this is in 3 dimensions. If we draw this model in 2 dimensions, as you commonly do it in chemistry, consider the nucleus. You always just draw a circle actually and shade, or sometimes just draw a circle. So we have here the nucleus, and composed of, or consisting of the, we have here the protons represented by the red and the neutrons. And then we have the first shell taking up 2 electrons, second shell taking up around 8, and then the last shell taking up the remaining electrons. So this structure is same as this, just because this is in 3 dimensions and this is in 2 dimensions. So to simplify life, we always draw in 2 dimensions. Now note, The number of electrons in the outermost energy level, or the shell that is outermost, determines the chemical properties of that element. So what are the terms that we use in atomic structure or even in the nuclear structure while studying an atom or a nucleus? Number one, we have what we call nucleons. Nucleons. Actually, I have a friend of mine from the north who calls them nucleons. Yeah, nucleons. If you look at nucleons, what are nucleons? Nucleons, if you said nucleons, you refer to, this is a general term which refers to both protons and neutrons in the nucleus of an atom. Now, you all know very well that the people in Uganda are called Ugandans. People in Kenya are called Kenyans. Particles in a nucleus, therefore nucleus, they will be called nucleons. So in other words, nucleons are the constituents of the nucleus. Number two, mass number, which we also call atomic mass and is denoted by capital A. Atomic mass or mass number is the number of protons and neutrons in an atom. So if you sum up the number of protons and the number of neutrons in an atom or in the nucleus of an atom, basically, because the protons and neutrons are in the nucleus. So when you sum up the number of protons and neutrons in an atom, you get what we call the mass number. Now someone may wonder, why? Why do we just talk about protons and neutrons? The reason is because the mass of an electron is almost negligible. It's almost zero. So we just leave it out. The electrons are so light in terms of mass, so light that their mass can just be taken to be zero. So when we are looking at the mass of an atom, we shall just look at the protons and the neutrons, which have some considerable mass, but the other particles, which are the electrons, have negligible mass. Number three, atomic number, which is denoted by capital Z, as the British call it. Atomic number Z. So this is the number of protons in an atom. Whenever you hear about atomic number, they'll be talking about the number of protons in an atom. Note, if capital N is the number of neutrons in an atom, then, now remember, mass number A is equal to the number of neutrons plus the number of protons. And yet we say the number of protons is equal to Z. So this means that when you get the number of protons, which is Z, plus the number of neutrons, you should get atomic number. So A is equal to N plus Z. Or A is equal to N plus Z. Don't forget that, please. Don't think about thinking about forgetting it. Number four, we have what we call a nuclide or a nuclear species. Yeah, but commonly in physics we talk about a nuclide. What is a nuclide? A nuclide is an atom with a specified number of protons and neutrons. So if you have an atom whose number of protons and neutrons is known, that qualifies to be a nuclide. You understand that? So we are saying a nuclide is an atom. Actually, you can say with a specified atomic mass and atomic number. Atomic mass and atomic number. So let's look at how we denote notation of a nuclide. Look at this. We will have the chemical symbol of an element, which actually I'm just putting as an X. And then up here, we put the atomic mass. Remember, A is the atomic mass. And then down here. But we put on its right, which is now our left. We are putting here, before the chemical symbol of that element, we put atomic number down and atomic mass up, where A is the atomic mass, Z is atomic number, and X is the chemical symbol of the atom. Let's look at examples of nuclides. So we have Na. Na is natrium, which actually is the sodium in English. Na, that is sodium. So we have a sodium nuclide, but to be a nuclide, the atomic mass has to be known and the atomic number also has to be known. So this means that the number of protons and neutrons is 23 and the number of protons is 11. We shall discuss more about that. We have Cl, which is chlorine and a chlorine nuclide. So still we have to know the atomic mass and the atomic number for it to be a nuclide. The number of protons and neutrons must be known. From here you can calculate the number of protons and neutrons. Even here you can calculate the number of protons and neutrons. Remember, down here this means the number of protons. Even here 17 protons in the chlorine atom, 11 in the sodium atom. And then this is the sum for the protons and the neutrons. So we want to look at the atomic composition and nuclear composition, which in other words we call the composition of an atom and the composition of a nucleus. So the composition of an atom, which we also call the atomic composition, refers to a specified number of protons and the neutrons in the nucleus and the number of electrons in the orbits of the atom. So when they talk about the atomic composition, they want you to tell them, if we ask you to tell us the atomic composition, we want you to tell us the number of protons, number of neutrons, those are in the nucleus, and then you tell us the number of electrons in that atom. And if we talk about the composition of a nucleus or the nuclear composition, we want you to tell us, we want you to specify, tell us the number of protons and tell us the number of neutrons in the nucleus. In simple terms, tell us the number of nucleons. Okay, I want to look at here an example. Describe the nuclear composition and atomic composition of the sodium nuclide 2311 Na. This is Na for sodium 2311. So the solution is very simple, like I'd already said. We said Z, this is the number of protons. So how many neutrons are here? The number of neutrons is just simple. It's very easy to calculate. Just get the number up here, which is atomic mass minus atomic number. So here, atomic mass minus atomic number gives you the number of neutrons. So the number of neutrons is 12. The number of neutrons is what? Is 12. And the number of electrons will be 11. Why? In an electrically neutral atom, we said the number of protons should always be equal to the number of electrons. So if there are 11 protons, it means even the electrons are also 11. Therefore, if they say they wanted us to describe the nuclear composition, you'll say the nuclear composition of sodium 2311 Na is, so we're going to say the sodium nucleus, because they're saying nuclear composition, you say the sodium nucleus consists of 11 protons, you see here, and 12 neutrons. Don't talk about electrons because they are not in the nucleus. Electrons are in the shells. They are not in the nucleus. Now, on the other hand, still maintaining the same information, the atomic composition of sodium 23, which is 2311 Na, is stated this way. The sodium atom consists of 11 protons. How many neutrons did we calculate? When we subtract 23 minus 11, we got 12. So we are saying the sodium atom consists of 11 protons and 12 neutrons in the nucleus and 11 electrons in the shell. Do you remember why we said 11? You remember very well we say that the number of protons should always be equal to the number of electrons. So if there are protons, if the protons are 11, therefore also the electrons will be 11. Yeah, very easy to remember. An exercise for you. Surprise. Describe the nuclear composition and atomic composition of the oxygen nuclide. I'm writing it 1680 with a big O. This is oxygen. 16 is atomic mass. This is atomic number. So describe the nuclear composition and atomic composition of the oxygen nuclide. Please, you can pause here and do the question before you proceed. Okay, welcome back to the I think this is the second last or the last slide. I want to look at isotopes. What are isotopes? Isotopes are atoms of the same element which have the same atomic number but different mass numbers. atoms of the same element with the same atomic number but different mass numbers. In other words, you can say isotopes are atoms of the same element which have the same number of protons but different numbers of neutrons. What makes atomic masses to be different, or the mass numbers to be different, would be the difference in the number of neutrons. So examples of isotopes, we have isotopes of chlorine. We have chlorine with the 35 up. You see the mass numbers are different. There is 35 and 37, but the atomic numbers are all 17. So those are isotopes. We have also neon, 10 down here for the same atomic number, but check the atomic masses, they are different. Hydrogen, we have 1 for the atomic number, but look at the atomic masses. There is 1, 2, 3. So these are all isotopes of hydrogen. We have isotopes of uranium, 92 as atomic number, but look at the masses. 235, 238, these are isotopes of uranium. Carbon, there is carbon 12, carbon 14. There is 12, 14, 7, 7. You see? Atomic masses are different, but the atomic numbers are the same. So these are isotopes of carbon. Thank you so very much. I request you to proceed to S4 Physics, Modern Physics Part 2, and we shall be looking at nuclear processes. I remain your host, Mandy Dennis, and this is my contact. Please, I request you to send the small exercise that I put there. Please forward your answer to my WhatsApp number 0775374719. The Airtel number is maybe just for calling. If you want to make a call, no problem. You can call for clarity. It's also here 0702744031. I remain Mandy Dennis. And please remember, I am making these videos free of charge. I put in costs. I incur the costs to process them. I actually had to buy the materials to make the videos. I am getting more gadgets to shoot videos better, and so that you people can learn together with me. So it's not evil if you think about donating something to this noble cause, as we are fighting corona together, having holiday coaching from home free of charge. Your donation is welcome. Please, you can send me some mobile money. Having some money from you is not a problem, and God will bless you abundantly. I wish you the best of the rest of the time. May God bless you. Let's jump into the next part.
Emirembe najibumba esanyu nalibumba nange kenyini namumba bumba nawe wosanga Yesu obone ebyokukaba sijuye byakusinda mukamani no mukwano.